Today's video will be on electricity. So this is grade 10 electricity. So this is our topic, electricity. So electricity is some sort of energy. So it's quite a huge branch of physics, and it's very interesting. So basically, for grade 10, you need to know is that in your problems they'll give you something, they'll call it a power source, and then the power source will be connected to some sort of a load. So a load is some sort of, it could be light, it could be your heater, your TV, even your smartphone, and they'll power source it, whatever that is charging or powering whatever that you're trying to power with electricity. Okay, so you know that. And then what is else? Okay, I have to go through some few terms that we'll be using. Mostly we'll be using something called current. What is current? Current is a rate of flow of charge, right, by definition, but I'll confirm with the study guide the proper definition that you're supposed to use. But just in simple terms, yes, I can just say it's just quantity of charge or number of charge. Yeah, number of charge is fine. Number of charge flowing or passing is fine. Fixed point in the conductor in 1 second. So remember the definition that I gave you was like the rate of flow of charge, of which is just the more scientific way of saying exactly that. So we know what is current now. So I think that I would to know current. Okay, also I have to mention that current is measured in, this is a symbol for current. Current is a rate of flow of charge per time. Yeah, rate gives time. Okay, so this is our formula, and the symbol, this is a symbol for current, and it is measured in something called amperes. A big A. So you'll see something like 10A, 2 amperes, normally small. If I have to be realistic, you can go use things like a milliamperes, micro, depending on the type of circuitry you're working with. So also there's something called, so current, we said current flow in some in some sort of a circuit, current flow in here, and some sort of conventional current direction. We'll look at that in the near future. Okay, so I think talking about current, we could have some sort of a problem that I'll try to bring out. Let me say I have an electric circuit with a current of 7.5 amperes. That's current, and then in that circuit there will be and that flow is passing per 3 minutes, right? Let me say time is 3 minutes. So you can see using this formula we have all the parameters, or we have all the variables that we need. So we can say this is time, this is current, so we can find the amount of charge. So the question for you, find the amount of charge. To amount of charge, you know that current is equals to charge over time. So I gave you current here, I gave you current to be 7.5, and I gave you Q. Q is exactly what I'm asking you to solve. So Q, just stay there, you don't know it. And then T, time, as in 3 minutes, but I don't really like 3 minutes in physics, we like seconds. So SI unit, right? We're not in America, so we have to keep in seconds. We use SI unit. Okay, so then we multiply, and then you cross multiply here. Remember there's 1 here, this one multiply this Q, you'll have a Q. This 3 times 6 will multiply that one, that's 7.5. and if you did very well in your calculator, you'll get 1350 coulombs. Remember I didn't tell you that this is measured in coulombs, a big C or a capital letter C for coulombs. So our next word or terms that we'll be using on our course will be something called potential difference. They normally call it PDs in some books. So potential difference, it's actually, as you can say, there's a word here, difference. That the word difference means you have to need 2 points. Okay, let me just draw some very simple circuitry. There'll be something like this. There'll be something like this. I think if you in grade 9 they did mention things like this, so I'm not. So for the record, this is the resistor, this is the resistor, this is the wire, this is the cell, the longer one is the positive, the small one is the negative, and this is the switch. Okay, so switch, it's like your tap or some sort of a valve. If you open or break, should I say, if like this is open, current can flow, right? So there'll be no charge going around the circuit because it's open. But when it's closed now, the charge can move and everything can happen. If there was a bulb here, it will switch on if the circuit is closed. I remember when I was studying this thing for the very first time, though I have some confusion saying that when it's closed, the circuit is closed, then now there is light, and literally in English you're saying closed like you're stopping something. So yeah, there's closing because the path is closed, the loop is closed, so now the current can go. So that was my confusion, but hopefully you don't go through that like me. Okay, so then what do I know? I want to talk about potential difference. Potential difference, exactly I said, it's measured across something. So I can measure a difference across these 2 points. In physics they love calling them nodes, but points, it's fine. There will be something called a voltmeter. Okay, voltmeter. A voltmeter is a device that you use to measure voltage, and an ammeter is a device that you use to measure current. Ammeter, amperes, current. Voltage, voltmeter. You see? Okay, so we can measure. Now we know what is current, we know what is voltage. Okay, cool, that's nice. We're building up. Okay, I said what is our potential difference by definition is the energy transferred per, that is my per unit charge that flows through it. So if there were charge here, whatever energy that you're trying to push through here, there's need to push through, passing through the resistor, that's a potential difference. It's like you're measuring potential energy here and comparing the potential energy here. You know what difference from math is the answer that you get after minusing. So actually you are comparing what is here and what is here. That's why I call it potential difference. Cool. So you said we use a voltmeter for that, and then because by definition potential difference is what is an amount of energy flowing to move a charge. So this energy is measured in joules, like you see in your food labels. The food give you how many joules and whatnot. And then for charge we already agree you have coulombs, and for volt you have volt. For voltage you have volt. Okay, cool. So I'll also do some very easy example also, so that you can see what I'm talking about again. I'll give you another easy example. So what if now you have 60 kilojoules of energy transferred to a 5k kilo coulombs. Okay, remember you bring up your formula. It's going to be V is equals to W. It's a big W, by the way, so big W all over Q. So you are given energy, you are given C, so you want to find what? Voltage or potential difference across that's whatever appliance that is in between. So there will be your energy will be 60 for kilo. No, kilo is 1,000, I need, so 1,000 is like just multiply by 1,000, and then if you multiply 1,000 you give it 3 zeros all over 5 kilocoulombs. So it's going to be 5 and give it 3 zeros, and then if you do something on your calculator here, you'll get an answer of 12 volts, which is a very normal number that you see on your adapters and whatnot in your normal use of electricity. So then what else? Then after all these terms that we have seen here, we are going to end up with something that we like as physicists, something called Ohm's law. Ohm's law, I normally call it VIR to remember it, where I have voltage here, I have current here, and then I have resistance here. The only thing that I even talk about is resistance. Okay, I have to say it. Resistance is some sort of something that opposes, it kind of opposes the flow of current. But by definition, resistance is a ratio of potential difference across the resistor and the current. And it's measured in something called ohms. This is a symbol. It's a Greek symbol called ohms, small letter O. It's a big ohms because the small ohms is written like this, so don't worry about that. Okay. Ohms, the symbol is omega. Why I'm saying omega like this? Symbol omega. This is it. So we know all the variables that are in Ohm's law. Okay. So this is what we call in Ohm's law. Ohm's law has a definition also, of which I don't want us to worry about much, but there is this triangle. Oh, why turn into a heart? There is this triangle, and then on this triangle we have this is a grade 9 triangle. You just have to fill in this formula in here. Let me show you how. So you'll have your voltage here, you'll have your current and the resistor. Let me say in the question you have to solve something like you want to solve voltage. You just hide this one, then voltage will be current, voltage will be current by resistance, as you see here. Let me say you're interested in something else beside voltage. You're going to hide something else. Let me say I want current. I'll hide current. Whatever remains, what remains, let's check. What current will be, whatever remains will be V all over R. So we know current. Good. Then let's try. What if we want to find resistance? We go there, we hide resistance. What remains? Let's check. If I hide resistance, what remains? I'm left with V all over I. That's nice. So we can actually solve for any variable that we need from Ohm's law. So our next part of the video will be parallel and series circuits. So series circuits is where series, like normally with things that you watch on Netflix, they call them series because they kind of add up. If something's a series, it adds up on something. So for instance, let me say I have a cell, and then I have a bulb and another bulb and another bulb. If you notice very well, these bulbs, they add up in one line. This is a line, they are on one path, they add up. So that's why they're saying they're connected in series. But this thing has some sort of disadvantage that if this cell dies, and then this bulb dies, all of them will die. Not like they will die, but all of them won't light up, because this one depends on this one. It's getting a current from this one. They are on the one channel. So they say it's one path or one channel, whatever you call it, one path. And then also, since there is one path, there is one current, meaning if you can solve for current here, you can find current here, you can find a current here. Also, what else to know? And voltage, I won't even say why, but voltage, because you'll see that on my example, voltage divide. So if this one supplies, let me say all of these were the same. If this one supplies 2 volts, Here this one will get, this supply is 6 volt, this one will get 2 volts and 2 volt, this one will get 2 volt. That's what I mean when I'm saying it's divide. It's divide according to the proportion of resistance, if I had to finish up my sentence. So if this gives 6, 2 will be here, 2 will be here, 2 will be here, and then they are dividing whatever that was supplied by a source. This is the load, remember from my first diagram that I told you about. Okay, and then there is parallel. Parallel is okay, parallel like this, and then now here there will be a bulb, there will be a bulb, yes. So this is a path, and then up around the way these paths divide. So remember there's a word called current. Current is like flow, it's like water. If this was a pipe and this thing opens up like this, that means some water will go in here, some water will go in here. That means on this case current will divide. Here voltage divide. Parallel current divide, because it's divides here. Current is water, it's divides here. And voltage, take voltage as some sort of energy. If they were linear like this, if this one takes energy, this will take another energy. Whenever remains will go here, whatever remains here. So this means we divide voltage here, then here we divide current. Also, if this one dies, this one won't die. That's a nice thing. The current also will divide according to the inverse of their resistance. Okay. Also, if this battery gives 6, let me say a cell gives 6 volt, potential difference between this and this will be 6. This means this will also be getting 6 volts, this will only be getting 6 volt, because here, let me write that one, voltage same. Here remember, current same. On this side current same, here voltage same. If current divide, then if current divide, voltage same. If voltage divide, current same. I think you can now spot the difference between parallel circuitry and series circuitry. When I have to finish up, I'll talk about resistance also. Resistance, both side resistance. Jesus, what I'm doing. And then both side. I'll talk about resistance for both. Remember the side we have, what do we have here? I think we have series here. Then we have parallel this side. So since the current is one line, for series connection resistance total, you can actually add resistor 1 plus resistor 2, resistor 4. Let me say 3. I was going to say resistor n, but I don't want to complicate my things. 3 again. What's happening? 3. Okay, on this side you can't really add like that. You have some sort of formula of which is saying resistors in parallel will sum up to the first resistor, inverse of first resistor, and the inverse of the second resistor, plus the inverse of the third resistor, depending on how many resistors you have. So if you understand these formulas and you can see what is the difference between parallel and series, looking at my notes here on top, I think you're really ready to go. See you on the next lecture.